So I asked you to go through the binomial and the multinomial and prove that they are maximum when the distributions are equal. So for example, for the binomial, when you're trying to divide n objects in two buckets, the number of possibilities is the largest when the size of the bucket is half of the number of objects you're trying to distribute. So n is n over 2. Similarly, if you have a multinomial, where a multinomial in this case, you're trying to divide in omega buckets, right? Or I think I called it R in lecture. Then the multinomial is maximal when the size of the bucket is n divided by omega, and all the buckets are the same. They are all of size n divided by omega. So I really hope you try to derive that at home, and remember that the way you do that is by you maximize not this quantity, but you maximize the logarithm of this quantity. Because if you take the logarithm, you can use Stirling's approximation, and then it's easy to take derivatives to find where the maximum of the function is. We can also say a little bit about how the binomial distribution looks like away from its maximum. And you can do that by expanding the logarithm of it around the maximum. So we'll do that here just for a binomial. So the binomial is maximum when the size of the bucket is n over 2. So if you do a Taylor expansion, which is what's done here, around the point of the maximum, and again, we're expanding the log of the binomial. So you'll find, of course, it's the value in the maximum, that's this function. The first derivative is 0 because you're in a maximum. And then the second derivative in the Taylor expansion, and I realize there are some things missing here. Excuse me 1 second, right? This needs to have n, this needs to have n one minus n1 star squared. So if you evaluate the second derivative, if you learn how to take the first derivative, which I asked you to do at home, you can take the second derivative as well, and you substitute in there that you're evaluating it at the point of the maximum, you'll find this simple expression that away from the maximum, you have the value of the maximum minus a quadratic, right? This is quadratic in the deviation from the maximum. What's now more important is when you go back to the distribution by taking the exponential, you find that the deviation behaves Gaussian. Right, so I got this by taking the log of the previous expression. Sorry, take the exponential of the previous expression. And now you see that this looks like a Gaussian, right? So the number of, sorry about that, the number of states away from the maximum is the number of states at the maximum with a Gaussian decay. And this is essentially a Gaussian with n being sigma squared, right? N being the standard deviation of the Gaussian. There's some interesting thing you can see about this, and let me go to a, maybe I can go to a new page because it's going to be hard to squeeze it on here. Actually, let me try to write it here and I'll erase it later. So if you're interested in relative fluctuations, so you're interested in like, well, what is the deviation of n minus n1 star normalized to n, right? So maybe you have a system with a number of particles n, and you're looking at sort of relative fluctuations of concentration. You will see that the probability of these fluctuations will go like 1 over the square root of n. And so while absolute fluctuations have this decay, what you will see is that relative fluctuations will decay as the system gets bigger, because the the fluctuations will go like 1 over the square root of n. And that essentially will be the whole idea of statistical mechanics, right? While systems fluctuate, if they are large enough, their averages will not fluctuate. And we'll come back to this again and again. And what you see is we sort of got to this conclusion without really any physics, right? There is no physics in here. This is really just the laws of large numbers. If a quantity is Gaussian distributed, then the larger you make the number of things that obey that Gaussian distribution, the larger the relative fluctuations become. We'll come back to this issue again. The last thing I want to show you is what's called the maximum term method. And now I should get rid of this because this doesn't belong here. The maximum term method is a fairly simple statement that if you have a sum of all terms that are positive, right, Tn is positive, and there are m terms, so then the sum has to be distributed between the maximum term or m time the maximum term, right? There are m terms, the maximum is T max. So if they were all equal to T max, then the sum would be m times T max. If all the other ones were 0 and only T max, then the sum would be T max. If you take the logarithm of that, which I'm doing here, you find that the logarithm of the sum is bracketed by the log of T max and the log of T max plus the log of m. Now in statistical mechanics, we will often deal with a situation where the terms themselves are much, much larger than the number of terms. So you're in a case where this logarithm T max is much larger than the logarithm of m. Often the things we're summing will be of the order of e to the power m. And in that case, this will essentially become negligible, which means that the logarithm of the sum is the logarithm of T max. I mean, this seems like an odd statement, but again, works almost exactly when you go to really large numbers. So what that means is that in some cases, we will want to do a sum of all positive terms, and the terms will be so large that all we care about is the maximum term. Okay. Okay, let me unshare here and we can go to the board. Oh, sorry, I need to make this track. Okay. So let me remind you the difference, how we define the difference or state the difference between macroscopic thermodynamics and statistical mechanics. So in macroscopic thermodynamics, you have a single equilibrium state. And for example, I could specify that by a certain amount of energy, volume, and number of particles. So this is macroscopic. So microscopically, that system fluctuates through many different microscopic states. So this is the microscopic view. This is the macroscopic view. And what I argue to you is that many of the extensive variables are time averages. They are the long-term time averages. So I would probably take t to infinity here. But in practice, we're going to replace the time average by what's called an ensemble average. And so what do we need to know? One is we need to know what is the ensemble. So what are the possible states? We need to know the probability of each state. I'm going to use the Greek letter nu for state often. And so we will need the probability of each state. And then we will calculate properties by using these probabilities, right? So then the average energy, for example, will be the sum over all the states, probability of the state times the energy in the microstate. And you can do this for energy, you can do this for other extensive properties like amount of something, magnetization, etc. Okay. So what is an ensemble? So an ensemble is the collection of microscopic eigenstates that are consistent with the boundaries. I gave you some example of that last time, the particle in a box, right? So the thermodynamic boundary condition there was that the particle had to fit in a box. And we actually literally, we calculate or actually gave you the typical eigenstates that can fit in a particle with an infinite potential wall. So the particle cannot leave the box. In practice, we will rarely be able to solve the quantum mechanical problem. So the ensemble definition will be a little looser and will essentially become all the possible microscopic states we can imagine that are consistent with the boundary conditions, right? So if we have a box of a certain volume, it's basically all the states that fit into that volume. We won't be able to actually calculate the quantum mechanical eigenstates. So, for example, if our boundary conditions are constant energy, volume, and number of particles, this has a name. This is called the microcanonical ensemble. Microcanonical. This will contain all microscopic states with that value of energy, volume, and number of particles. So all state with the same energy, volume, and n. If on the other hand you do thermodynamic boundary conditions, applied boundary conditions, say T, Vn, so in classical thermodynamics you would do a Legendre transform. So when you're in a temperature environment, you can now exchange energy. So constant energy is not a boundary condition. This is called the canonical ensemble. And this is now all states with the same volume and number of particles that are specified by the boundary conditions. But we cannot specify the energy because the thermodynamic boundary condition allows the energy to fluctuate. So in principle, this ensemble is larger, right? Because let's say I take the same volume and n in a microcanonical ensemble and a canonical ensemble. The canonical ensemble includes all the microcanonical ensembles for all the possible different energies, right? Because the energy can fluctuate in the canonical ensemble. And I can keep on going, right? If I did constant T, V, and mu, so now I only have one extensive variable as a boundary condition. This is called a grand canonical ensemble. And this is now all microstates. The microstates now only have one specification, and that's that they have to fit in the volume. So again, if this volume were the same as the one before, then the grand canonical ensemble includes all the canonical ensembles and all the microcanonical ensembles. So you can sort of see a system coming here, right? Come on, camera. So for each set of thermodynamic boundary conditions, you would be able to construct a thermodynamic potential, right? That's what you've learned so far. And the equivalent in statistical mechanics is a specific ensemble, right? So this would be all constant extensive quantities. And remember, for this thing, the entropy is maximized, right? So for each set of boundary conditions, there's a thermodynamic potential and there's an ensemble. And as we work our way through these lectures, we'll show you how the properties of the ensemble will determine the properties of the thermodynamic potential. So for example, you know, microcanonical, canonical, and grand canonical are the ones you find in books, but we could define new ensembles, right? Let's say I have applied boundary conditions T, V, N, and H. Right. What you know from thermodynamics, right, that to get the potential of this, you would Legendre transform the energy with respect to Ts and Hm. So your thermodynamic potential would look something like U minus Ts minus Hm, right? And by now you can calculate the differential of that. d phi would be minus sdt minus mdh. In statistical mechanics, we will often work in entropy notation, but I'll go through that later. So what would be the ensemble? Would be states with the fixed extensive variables in the ensemble, so with fixed V and N, but magnetization and energy could fluctuate. Okay. So once we define the states, we now have to get to the probability of a state. So the question is, how do we find the probability of a microstate in the ensemble? Because once we know that, then we can in principle do this sum over all the microstates of any property, right? I could take any extensive variable in the microstate and that would be my average of X. So figuring out what the probabilities are is, I hate to tell you, it's going to take us this lecture, the next one, and more. So we're going to build that up first for specific ensembles, and then we're going to do that more generally. So it starts with a postulate, which is practically speaking, I think the only postulate, well, no, it's one of the two only essential postulates of statistical mechanics. The first one is called, and I should have given you that 2 minutes before is called what's called the ergodic hypothesis. And the ergodic hypothesis basically states that if you wait long enough, a system will visit its whole ensemble. So if you wait long enough, system visits the whole ensemble. I really should say, to be more accurate, every state in the ensemble. The reason I should have given you that earlier, this is the reason you can replace the time average by the ensemble average, right? If I had a system going through my microscopic phase space, through my ensemble, and let's say I constructed the strangest system where the system kind of stuck in a loop. It goes between 5, 6 states and just goes between them and never gets perturbed out of them, but never visits any of the other possible microstates. That would be a violation of ergodicity because the time average would not be the same as the ensemble average. And people spend a lot of time worrying about violation of ergodicity. But what we know is that for any practical system we ever deal with, ergodicity is satisfied. You can create some odd systems that are not ergodic, but in general, this is true. So how do we get to probabilities? The way we define we get the probabilities is starting from a true postulate, which is called equal a priori probabilities. And this is the first postulate, the first real postulate of statistic mechanics, which is a remarkable statement. And it says that for a system with constant energy, so a microcanonical ensemble, all microstates are visited equally likely. So basically they have the same probability. I mean, think about this. This is not a trivial statement, right? It's basically saying that, you know, if I have a bunch of possible microstates, I really don't care about any property of them except the energy. Only the energy determines how often they're visited. I mean, my guess is that you intuitively believe this because we're so used to, you know, we're so used to using energy, right? Oh, things go to low energy and, you know, excitations happen with Boltzmann's factors and blah, blah, blah. So we're so used to using this, but it's actually not obvious when you think about it. And the reason we derive all these things like Boltzmann factors, and we'll come to that in class, is really because of the equal a priori probability. If this were not true, our world would be remarkably complicated. So what does that mean for the microcanonical ensemble? So if we do microcanonical, so let me call omega the number of microstates in that ensemble. And it's, of course, it's a function of the boundary conditions, right? Then what's the probability to be in a given microstate? Well, if they're all equally likely, then the probability to be in a given one is just 1 over omega, right? It's 1 over the number of microstates. So we can now do trivial math. Let's say, what's the average energy? It's the sum over all the microstates times the probability of the microstate times the energy of the microstate, which is a sum over omega terms of the probability 1 over omega times the energy. So it is the energy of the ensemble, right? This is sort of a trivial rederivation, right? All the microstates have the same energy. They have probability 1 over omega, and I sum it omega times. So the average energy is the energy of the ensemble. So there are some trivial implications of the microcanonical ensemble. And one of them is that the state that you macroscopically observe, so the macroscopically observed state will be the one with the most microstates. So let me give you an example of that. Let's say we have a non-interacting gas. So we have gas atoms in a box. And it's a fixed box. It's not interacting with the outside world. And I want to look at two macroscopic states. So my label A and B is the label of a macroscopic state. And the first one I'm going to define as, in words, the atoms are homogeneously distributed in the box. Right? So this state I call the homogeneous state. And the other one that I'm going to define as the atoms are all in half of the box. So I could draw like a virtual wall, not a real one. Right, so this is virtual. And in this state B, all the atoms or gas molecules are in half of the box. So which of these macroscopic states will I actually observe in thermodynamics? You all know that I'm going to observe A more, right? But the question is, why is that? Because the only reason that is the case is because there are more microscopic states like this than like that. If I take a specific microscopic state, so I'd now take a state where these dots are exactly where I put them. What's their relative probability? So now I'm asking about the relative probability of these two microscopic states. What's their relative probability? Don't all jump.
Are they equal?
Yeah, they're equal because they have the same energy. remember, I am in a microcanonical ensemble. All microstates have the same probability because they have the same energy. So these very specific microstates have the same energy. So why is there a difference in the macroscopic observation? It's because the macroscopic observation is a sum of all the microstates that correspond to that observation. So let me write this out. So what is the probability that I observe B? The probability that I observe B, I'm going to sort of write this out with words, is the sum over all the microstates, but restricted to only the ones where atoms are in half the box, right? Can you read this? So I'm only summing over the microstates where the atoms are in half the box because that's my macroscopic definition of the states. Whereas PA, I don't have a constraint on it. So this PA is just the sum of all the states. And since there's just a lot more here, so maybe I'll call this omega B and this omega A. Since there's a lot more here, this is going to be much larger. I think in the problem set, there's actually a problem where we ask you to calculate that. So what's the important takeaway message here? Even though these states have the same energy, the specific microscopic states, when I turn this in a macroscopic definition of a state, right? My macroscopic definition of a thermodynamic state is not the atoms are in this specific place. My macroscopic definition is the atoms are homogeneous. They're spread out over all the box. That sums a lot more microscopic states. So why do I see, in the end, if I ask you the question, when I put atoms in a fixed adiabatic box, why do I see the atoms spread out? Why is that my microscopic state? The answer is it's just because there are a lot more microscopic states like that, right? The reason I don't see this, the reason I don't see this is not because these states have high energy. They actually don't. There's just less of them. And what I see is a time average. And since this happens a lot more, this is what I see. PA. And you know, if I could sum up statistical mechanics, it would essentially be this. The macroscopic state that you see is the one that occurs most of the time. That is essentially statistical mechanics. So in principle, why do I stand on the floor? You know, there is a finite probability that I would levitate, right? That state has a non-zero probability. But it's because the microscopic states that have me attached to the floor, there's so many more of them than the ones where I levitate in the air. And when you go to the laws of big numbers, right? When you go to macroscopic systems, that ratio essentially becomes zero. So the probability that I actually levitate becomes almost zero, just because of all these binomials that we have talked about. So you will see now where entropy comes in, which is in some derivations of statistical mechanics, the second postulate. And this is the way Chandler does it. He introduces entropy and the Boltzmann formula as a postulate. In some more complex derivation of statistical mechanics, this is actually not a postulate. You can actually derive that. But let me for now follow this. So the second postulate is the Boltzmann law. That the entropy of a macroscopic system is KB log omega. Right? And omega is measured at constant EVN. And so the entropy is specified at that EVN. So remember, this is due to Boltzmann, right? And if you think about it, this is really like something you could have come up with. Because if you want to build a relation between entropy, which you've learned from classical thermodynamics, is an extensive quantity, and number of configurations, it actually has to be logarithmic, just because of the nature of combinatorics. And let me tell you why. If I take two systems, and I'll call them A and B, and they have nothing to do with each other, so they're both isolated. So this would have an omega A, and this would have an omega B, a number of microstates, and I could define the entropy of them. SA is KB log omega A, and here I would have SB is KB log omega B. If I now look at them together, but not mixed, so I look at them as one system, again, isolated, they are not interacting within the system. I just take A and B together as a system. What is omega of this system? So what is omega of the mixed A plus B system? Think about that. What is the number of possible microscopic states for that system? Remember your probability theory, statistics, whatever you call it?
Are you letting them like mix, or are we just considering them as one?
So they remain separated. I'm just looking at the join. I have a system that's the joining of the two systems.
Just the product of their omegas?
Yeah. So the number of microstates is the product of omega A, omega B. And the reason is, so now microstate is a specification for A and a specification for B, right? So here I have omega A specifications, and for each specification here, I can pick one out of here. So here I have omega B, so the product is omega A, omega B. What do you know about the entropy of this? Because entropy is extensive, the entropy of A plus B has to be the entropy of A plus the entropy of B. Right? Because they haven't interacted, so the entropy just has to add up. So how do you relate these? You have something that follows a product rule, and then you have something that's additive. They have to be related to a logarithm, because right, the logarithm of products is the sum of logarithm. So Boltzmann's equation is really the only one that satisfies extensivity. So this was a brilliant insight of Boltzmann, right? That, you know, the entropy couldn't be something complicated of the number of states. It couldn't be, you know, 3 sines and cosine squared, right? It had to be the logarithm. And I'm going to show you towards the end of this lecture that this is brilliant, right? That everything you know about thermal physics comes from this logarithm. And it's there for such obvious reasons. Okay, let me do that now. Have you done with the board? Because I need this board. But it's so beautiful, I can't erase it. Okay, I'll turn it from the back side. So what we're really interested in is what happens in a canonical ensemble, right? Because in a canonical ensemble, the energy can fluctuate. And what we really want to know is what's the probability of higher energy fluctuations, right? So for that, we have to know the probability distribution in a canonical ensemble. So there are two derivations to this. One of them I'm going to give today, that's the Chandler's derivation, which comes out of Chandler's book. If you have the same book, it's in Chandler, page 62. And Chandler's derivation is brilliantly short, but it uses the Boltzmann law. So this one makes use of S is KB log omega. There is a more classic derivation of canonical ensembles, which is much longer and which is in Macquarie, and which I will do next lecture. It's hairy. It's going to take us a whole lecture. And that's why I want to keep a lecture set aside for it. And it does not use S is KB log omega. So in some sense, it's a little more fundamental that you don't need the second postulate. The Chandler one is beautiful, and that's why I want to give it to you. But I want to give you the official derivation next on Wednesday, because that's the one that everybody else will know and everybody else will teach, and you have to know how to go along with the crowd. So, I mean, you have to know what people talk about in statistical mechanics. It's also the one we will use to extend to other ensembles. Okay, so let's go for, today we're going to do the Chandler derivation. So what Chandler does, so this is my canonical ensemble, my canonical system. And it has a certain energy, E nu. And what I want to know is what the probability is of that energy. So the way he finds that is by embedding the system in a much larger system, a heat bath. And that one we will consider to be microcanonical. So the larger system, this system is constant energy. Which means that the energy, if this has, let's say, constant energy E total, if you have energy E nu here, then the rest of the system has E total minus E nu, right? Does this sort of like does this look like something you do in thermodynamics? Right, very often in thermodynamics, when we don't know how to define the equilibrium on a system, we just go to a bigger system where we can actually control the flows over the boundaries. Okay, so all states in this microcanonical ensemble have to have the same probability, right? Because it's microcanonical, they have the same energy. And that's going to allow me to make a statement about how often this fluctuation occurs, right? What we really want to know is how often is energy E nu concentrated in this aspect of, in this part of the system. So the probability to have energy E nu in the, I'm now writing the probability to have a certain energy in this subpart of the system, has to be proportional to omega E total minus E nu. Why? Because the frequency by which E nu occurs is the frequency by which this occurs in the rest of the bath. And I'm going to write that, so this is omega, I'm now going to write that as the exponential of the logarithm, right? So nothing gained here, of omega E total minus E nu. Okay, this is just math, right? I take the exponential and the logarithm, but the reason I want to take the logarithm is because I want to Taylor expand the logarithm, and I want to get Boltzmann in there because the Taylor expansion of the logarithm is going to get us to entropy. Okay, so I'm going to Taylor expand now. I'm going to Taylor expand the logarithm of omega around the logarithm of omega of E total. Okay. So the logarithm of omega evaluated at E total minus E nu is the logarithm of omega at E total minus E nu. That's the perturbation, right? That's how much I go away from E total times the derivative of d log omega energy with respect to the energy. And I want to evaluate that at E total. And this is getting interesting, right? Because what do I have here? I have the log of omega, which is essentially entropy, right? Up to a Boltzmann constant. So I'm having a derivative of entropy with respect to energy. And if you remember a bit about the first part of our lectures, you can figure out what that derivative is. Right? So because we have S is KB log omega. From thermodynamics, we know that the derivative of energy with respect to entropy is T. Right? That's the remember the equation of state. That's the equation of state coming from the internal energy formalism, where we call this U, right? Now it's called E. Okay. So what that means is I'm going to invert this, right? So that means that ds dE is 1 over T. And ds, S is KB. So what you get is that KB d log omega dE is 1 over T. So d log omega dE is going to be 1 over kBT. So this bad boy here, right? This here is 1 divided by kBT. In statistical mechanics, we will often use the notation beta is 1 over kBT, right? Just so we don't have to write kBT all the time. So let me now take the exponential of this here. So now I want to take the exponential so I can get rid again of the logarithms. So you take the exponential. And what you get is omega, the number of states of the total system, of the complement to the subsystem that are E total minus E omega is omega E total times the exponential of minus beta EV, E nu. So since this is some constant, what it means is that the probability of a microstate is proportional to the exponential of minus beta E nu. And so what drops out is the Boltzmann factor, right? It's proportional, and the way we can get the normalization constant is by we can require normalization of the probabilities. So sum over all the probabilities has to sum to 1. That means that sum over all the probabilities, P nu has to sum to 1, which means that the probability is really equal to the exponential of minus beta E nu divided by the sum of all these exponentials, right? And maybe I should use a dummy index here. Maybe I should call this I. Right, so this is the proper expression to normalize this. And this object is called Q, is called the partition function. We will later see that it has a much more important role than just being a dumb normalizer. It turns out that it's sort of the function that contains everything you need to know about systems. Can you read that? I'll go back down. Okay. So we took the log here. That means that the probability, right, because the probability is proportional to omega, right, how many states there are in the bath, is proportional to the exponential of minus beta E omega. Once we have a proportionality relation for probability, we formally have the relations because we always know that sum over all the states, probability has to sum to 1, right? So I could write this as the probability equals some constant, right, times the exponential. And then I require that sum of the probabilities equals to 1. So I would find that this here is 1 over C, right, that constant. You know, I want to pause here for a second because this is, I mean, it really is beautiful, right? All this stuff that you've seen for many years in physics, in chemistry, in science, that probabilities for events are proportional to a Boltzmann factor, right? They're proportional to the exponential of minus beta some energy. That's actually not as obvious as you think, right? And where does it come from? I mean, there's not much you need here, right? So it comes from two things, right? It comes from, you start with equal a priori probabilities, which is essentially telling you that energy is the coordinate for probability. It's telling you that if I know the energy, that determines the probability, nothing else. That's one thing. And the second thing is the Boltzmann term, right? Because when I do this expansion here, the Boltzmann term is what makes 1 over kb t appear, right? So the Boltzmann term is telling us that it's the energy weighted by kbt. It also tells us that the form is exponential. So it's kind of remarkable how just two things like give you this sort of exponential relation. Any questions? Okay, now for the bad news. We graded your exam. You can turn